Yeah, you have to make z equal to a. So remember, this is the one that was just like the beginning of notes yesterday. Oh, guys, I know. I was letting you guys talk, but now it's my turn. This is like the one that we started from yesterday where we have 3 unknowns, only 2. So I'm not going to go through explaining everything. It was basically exactly where we started notes yesterday in 7.3b. But what you wanted to do was probably eliminate the x, because we can still do sum. So I would multiply everything by a 2. I would have ended up with 3y plus 2z is equal to 3. In my row echelon form, I could have gone ahead and used this guy, dividing everything by 2 to make it all nice and proper. Then I could have used that guy, dividing everything by 3 to make it proper. And the problem was we had no way to keep going and get our other y's and z's to get our just z's. But the reason is because there are infinitely many solutions. Remember, the 2 planes can't hit in one point. They keep going. It would hit in the whole line. So this is one of those examples where you need z equal to a. So some of you might have gotten a bit messed up as far as the fractions. Maybe that was the hard part if you were following our example from yesterday. So when you go to solve, remember, you already have your a. For z, we plug that back in to get y. So y is equal to 1 minus 2/3 a. And then it gets a little bit messy because now we have to plug both of these guys into the top equation. But I just think it's safer to write everything out. So x minus 3/2 times who y is plus 1/2 times who z is. And then we just have to kind of deal with our fractions unless you want to get rid of fractions by multiplying everything by 6. Joe? Then I don't want to hear it quite yet, so just remember it, and I'll ask you in a second. So then as we keep going, x minus 3/2 plus the 3 and the 2's, they all reduce. So plus a plus 1/2 a is equal to -1. I'm going to add 3/2 on the other side, which -2/2 plus 3/2 is 1/2. Then I can put these together to be 3/2 a or 1.5 a and then subtract. So I'm going to end up with 1/2 minus 3/2 a. Now I did a lot of fraction work in my head, so if you guys wouldn't mind double checking. And as you check, we're getting ready for number 47. Now go ahead, Joe. What's up?
What if like when you try to simplify it and you find out you can't eliminate both x and y and you let that type of number?
Well, that would just be one step of the system. So you would still technically, if x and y, creatively, since you're not a computer, you can take this and solve for x's and y's. So you can do that. You see what I mean? So you can cut the process a little bit. Yeah, but you still have to go looking for x and y. Matthew? But that's what we did. We did solve for y. And we did plug in for what we got for y.
How come you have to make z equal to a? Like, how come it's a? Like, why can't you just be x?
Well, the problem is x is already being used, bud. So you're right. In math, we do use variables for unknowns, but x is very specifically this unknown of these equations. So I can't use x. He's already been used. I can't use y. I can't use z. So typically, if the x, y's, and z's, if the latter end of the alphabet aren't working, just in math, they usually go to the beginning end of the alphabet.
You're to solve for one variable, and you have another variable like y equals 3x. Wouldn't we have z equal to x because we're writing in terms of x?
No, we're not writing in terms of x. We're trying to solve for x equals. So we can't x equals himself. That doesn't really help. See what I mean? Yeah. And since there are infinitely many solutions, we have to have them all in terms of some number that can change to get us more and more and more and more and more answers. But x and y's and z's are in actual points in space, and so I need them to maintain their meaning of x is a horizontal, y is a vertical, z is a three-dimensional. I need them to keep their meanings. And not just another, but also relative to space. I need them not just to be relating to each other, but relate to all the space around them. That's why we have to go use another variable. Keep pondering. Keep pondering. Yeah, I see that question on your face. Vertical motion. Vertical motion. This is the hint that I had you guys looking at in the notes just a second ago. And I had this formula in your notes, and I said basically when they give you 3 points, you have to plug in your 3 points. Instead, if you don't like A and V and S, you can make it X and Y and Z. If you don't like A and V and S, you can make A equal to X, you can make V equal to Y, technically V sub naught, and you can make S equal to Z. So I say not because another way, 0, or lots, there are lots of ways of okay. So let me go ahead and show what I would have gotten if I had followed my own advice of plugging in an S and a T and then making my weird letters into normal letters. The first equation I would have gotten is 128 equals 1/2 x times 1 squared, so 1, plus y times 1, which will just be y, plus z, well there's no t to even multiply, so z. I would have plugged in the 80 times x times 2 squared, so 1/2 times. We'll come back to that in a second. And then plus y times 2. Y times 2 is 2y, plus z times nobody. And then we would have plugged in s is when t is 3, so 1/2 x times 3 squared is 1/2 x times 9, plus y times 3, which is 3y, plus z times nobody. Now, that's true, but it's not written in a I don't think so. So let's rewrite them. Does anybody else agree that we should multiply by 2 to get rid of that guy? Yeah. And then, wait a minute, hold on. This one, 4 over 2 already reduces, right? Okay, so let's not worry about multiplying that by a 2. I think he'll be good if we just simplify. And also, guys, when we do systems of equations, don't we usually want the equals over on this side? Yeah. Okay. So it'll be a little bit easier on our brains and to rewrite this in a system that you guys would be able to better solve. And then I'll let you guys go solve it. Probably, I think the hardest part is getting it written out. Move the 256 times 128 over here. I'm going to distribute my 2, which will cancel out and still be there and still be there. So 1x plus 2y plus 2z equals 256. 80 is going to come over here, and I get 4 over 2 is 2x plus 2y plus z. And last but not least, 0 is going to come over here. Uh-oh. Does 9 over 2 reduce? No. Okay, I think I'm going to get rid of that fraction too, if you guys don't mind. 2 times 0 is still 0, so I'm fine with that. But when I come here, the 2's will reduce. I'll 6y and 2z. Is this something that's a little more normal to solve now? Yeah. So once you have that system of equations, I would just keep going from there. And probably the odd work and the calc chat work, even though they do it a little bit differently, should at least somewhat measure up with eliminate the x's, eliminate the x's, eliminate the y's. There's z. End of the day, guys, when you get z equals, just remember x was the a, y was the v, z was the s. And then there was one more question, number 59. Where's my football guys? Some of you just kind of played around with the numbers in your head until you figured it out. Or even my yeah, right? Because you can kind of just play around with the score. Some of my non-football people are people that were like, no, I wanted to actually know how to do it. You have to take your clues. I mean, they tell you it was Super Bowl I. They tell you who was playing, what year it was played, etc. But pulling out the actual clues as far as the solving of the problem, I know the score was 35-10. Maybe that's why my dad was a fan. Back in Super Bowl I. Anyway, the total points scored came from a combination of touchdowns, extra point kicks, field goals. For those of you guys that don't know football, touchdowns are the 6 points, and then extra point kicks, that's the 1 point, and then the field goals, that's the 3 points. Just telling you who's who. The number of touchdowns and extra point kicks were equal. I I think they meant for us to make some unknowns, like an x and a y and z, yeah? So could we maybe say, we don't know how many, touchdowns? We don't know how many extra points without like thinking it through and playing around with different number combinations. For our x and our y and our z, okay, that's better. The number of touchdowns and extra point kicks, so x and y were equal, okay. Yeah. What else? So 6 times as many touchdowns as field goals. But wait a minute, hold on, wait. Does this make sense? Isn't this saying the number of field goals were 6 times the number of touchdowns? Does that make sense? It doesn't make sense. Yeah. Sometimes just taking the order of the numbers as they appear, 6 times touchdowns, 6 times as many touchdowns. The touchdowns were 6 times the field goals. It's a little rough sometimes. The English gets a little funny if you don't fully understand what it's saying. There were 6. Did I not deal with yet? The score. Every touchdown got 6 points. Every extra point kick got 1 point. And every field goal got total points of the game. Does that make sense? You have to have 3 clues with 3 unknowns. Now some of you, yeah, I could play with this. Yeah, you could play with this. But another way of doing this, you could go x plus y plus 3z. Get your system written the way that you're used to. Subtract the y. X minus y equals 0. Subtract the 6z. X minus 6z, or I should say. That looks a little more normal. You could solve it the way that you were supposed to be practicing from our section. But if you familiar with football. Guys, it isn't odd. You can go and check out how they've solved, how they've finished. But I think the hardest parts on both of these, once again, was just figuring out the system. And then just do what the rest of homework had you do as far as solving. Matthew.
You really have to solve to write those equations in row echelon form because you already have x equals y. So couldn't you plug that in?
Yeah, but follow that logic. If we did plug in x equals y, then we have y's and z's and x's and z's. It doesn't match up. If we plug in z, then we have y's and z's and x's and y's. It doesn't match up. So in some way, shape, or form, we're going to have to work with more than one. You could technically, one way, I wouldn't go straight here. Try to do a shortcut. I would go here, substitution. Because what could ignore that guy? What could I do down here? I could say y equals 6z. Then I could come up here, make y equal to 6z, and then maybe that might work. But don't go straight to plugging into the top equation or you're going to get in some trouble. Okay, we're going to section 7.4, but wait, do we even know what the answers are to the evens? Here we go. 30, you guys already saw. The final answer was a false statement, which means inconsistent, no solution. Number 50, you would have wanted to use your 3 points like we just did with position, but everything was nicer because you had x's and y's already. Well, the x's and y's actually got plugged in for. So what you got were a's and b's and c's. Still a system of equation, just your letters were different. But you could have gone ahead and like played around with these. You could have tried to make a system of 3 equations and solved the long way. But if you guys noticed, plugging in this guy actually got you C. So you kind of cheat, not cheat, but like what Joe said earlier, if you already have Z, if you already have C, plug them into both and be like, yay, it's easy. And then finish. And once you got A and B and C, it was your parabola, and all they were asking is if the answer, number 64. After solving, should have landed you on z equals 94. In context, 94 degrees. Back substituting, got you x equals 36 and y equals 50. So once again, in case I went too fast, I thought I might have at least felt groans, whether or not you guys said it out loud. For number 50, A was -1, B was 2, C was 3, after plugging in 3 points and solving the system. So your parabola was y equals A, -1x squared plus B, 2x plus C plus 3. 64, final answer was 94, 36, 50, but that's not in order. I would have said 36, 50, 94. Done. Anything else quick you guys want some clarification on? Going once, going twice. We got the hard ones and the odds? I gave you the hard ones and the odds? How come? So you could check. All right, you ready? Let's go. 7-4. Nice thing is, oh, I didn't write it on the backboard. Sorry. On Tuesday. I think I said something about that yesterday. Sorry, I didn't take roll yet for you guys. What's going on? We're good, we're good, we're good, except for one. Yeah. Just Tyler's missing. All right, thanks, kiddos. 7.4 partial. Ooh, that page is nasty. Let's zoom in on this page. All right. I know, it's all nice and warm, but now you're all falling asleep on me. It's a little illegal, but it's warm in here. Section 7.4, to write a rational expression. Rational, ratio. This sounds like chapter 2 or chapter 1. Aren't rational functions the ones that are fractions? And the answer is yes. Aren't rational functions the ones that are fractions? And the answer is yes. Let me give you just a moment to write down the first page. And I want you to peek at that example. And my question to you is, how could you know that those two sides, the left side of the equation and the right side of the equation, how could you know they're the exact same thing? Well, they are already equal to each other. How could you show they're the exact same thing? Don't worry, it's not exactly a T-proof, but you kind of have to think that way. Okay, pause. Shh, let people take notes. Thank you for the answers, but hold on. Think about it. Think about it. Don't talk about it yet. But good. Keep thinking. All right. Who wants to raise a hand and kind of talk it out loud and clear as to how they think I could show you that these two are the same? Matthew, go ahead.
So what you could do is you could FOIL the bottom, so that because it's just the vector form.
But I can't FOIL if there's a plus, though, can I? Oh, I like the wording. Matt, his head was like, what if you FOIL the bottom? But then you can't just randomly FOIL two different denominators with a plus in between. He said common denominators. Because to get common denominators, wouldn't you multiply them by each other? Right? So kind of think about a T-proof. Don't worry, this is not a T-proof section, but kind of think about it. So if I was to multiply this guy by x plus 2 over x plus 2, and multiply this guy by x minus 3 over x minus 3. What's true about my denominators now? So I can put that all together. And up top, I could say 2x plus 4 minus x plus 3, which would be 1x plus 7. Nice. All I have to do is FOIL. And what do you guys think happens when I do first, outer, inner, last? Okay. Have you ever, in your math career, had to take something and make it look like something like that? Yeah, totally. Tons. I don't know, maybe. When we were doing like horizontal asymptotes and stuff in chapter 1, I wanted you to get common denominators to be able to do degree tests and stuff like that. We might not have seen very many that were too complicated or too rough where we had them written separately and we tried to put them together. But there were some of those. However, here's the weird thing about this section, guys. You're not following that blue arrow that I just wrote up. Right? That's not the direction of our thinking, of our moving, or of our solving. This section says, not from here to here, but from here to here. Taking a whole and splitting it up into his parts, partial fractions. Taking a whole, a simplified rational function, and breaking him up into simpler parts. It's not going to totally answer all of your questions. I have some very curious brains in here. If you want to at least hear something about how this applies, go talk to a Calc BC and be like, do partial fractions come back? Guess what they're going to say? Yes. Were they useful? Well, they might be a little bitter about it, but if they were honest, they would say yes. For Calc BC kids, some harder problems from Calc AB are made possible only by being able to do this, which technically is a pre-cal skill. So they had to review partial fractions. So we're not going into all the crazy of exactly how it's used, but I want you guys to think of something. Is there any just life lesson, just in general, is there any place in life where it might be useful to take something complicated and figure out how to break it down into simpler pieces? Oh, kind of sounds like it. Imagination station? I mean, no. Conjunction function? What? What do you think, Matthew? Yeah. Not just computers either. Cars, same thing. Now, you do have to be careful of what you're taking apart. Yeah? If you don't know how to put it back together and it's something you need to do, you better be careful with that. But some people learn best by seeing something put together and taking it apart. That's a very common way of learning. Joe, did you have another one? Taking something complicated, it's going to be helpful to break it down? Oh, planning for a trip? Like you know what you want to do, but you actually have to think through each of the individual, break down the details. That's true. Spread it all out, especially if you're like chaperoning your trip. Ooh, that's even scarier. Coming back. But in math, though, let's see. In math, where else have we done this? Taking something complicated and broken it down. Simplifying, that's one way. In T-proofs, didn't I give you something really complicated and sometimes it could be broken down into something simpler? One way. Where else in math? Something complicated we break down. Condensing and expanding with logarithms, maybe. Taking something all written out and putting it in and then taking something all in and writing it out. And that was actually super applicable for solving equations because sometimes with equations we need it all written out and sometimes we need it all condensed in. Anyway, maybe we won't fully get to see all the applications. It's okay. Maybe we won't fully get to see all the applications of this other direction of thinking this year, but at least the idea of taking something complicated or condensed and breaking it apart, that general skill, hopefully at least somewhat rings a bell. So, what is this? If you guys don't mind, I'm going to be weird today. I mean, I'm always weird, but I'm going to be a little bit weird today in how I cover this. I just skipped over the big old page of all the complicated steps, right? And what am I on right now? steps, but looks kind of short and sweeter. Yeah? Okay. Let's do the short and sweeter version. Let's do an example with the short and sweeter version. Then let's go back to the longer version and see if there's any little fine details that we should maybe pay attention to. I don't want to totally overwhelm your brains. So we're doing the short, sweet version first. Ooh, and that line is way thicker than I wanted it to be. Why am I putting a line right here? Because technically in the very complicated wording, too thin, on the page before, it doesn't just say greater than, it says greater than or perfect. Make sure you write greater than or equal to. Divide. Huh? Why are we oh, long division. If we have a numerator, if we have a denominator, no, it's going to make it easier, I promise. If you're looking at a rational function, trying to get it broken down into its partial fractions, you need to see if it's improper. Improper, wait a minute, hold on, we know improper fractions. Improper fractions, that's like elementary school. What if you have something like 7/4? Is that improper? Yeah, it's top heavy. Why? Fractions are supposed to be parts to wholes. Why would you show 7 parts to 4 wholes? It doesn't make sense. Why would you say, hey, there's 1 whole and then there's 3 extra pieces? Do they mean the same thing, though? Yeah. And why would you show 7/4 instead of 3/4? Well, the piece, you have 7 slices. Right? 7/4 versus 1 3/4. Same thing with rational functions, but this time it's not just numbers. We have variables, and so how do we know if a rational function is improper, is top-heavy? It's all about the degrees. Not about how many terms, not about how big the numbers are, how small they are, whether they're positive or negative. It's all about the degrees. It's the weird thing. Greater than should make sense in your head. Top-heavy, the degree of greater than. But what's the weird part? Or equal to. If there's a tie, okay, you're thinking about horizontal asymptotes and degree tests. But if there's a tie, we're still going to divide, which is going to be kind of weird in your head. But guys, when you divide, almost always, the top goes in the box. We have the bottom outside. We're looking for any whole, put some new, I don't know, like f of x. But we're ooh, no. Right. Silly me. Remainder over that outside piece or that. So we're looking for any whole pieces, like you do with an improper fraction. Look for any whole numbers and then what's left over. Same thing with division. Look for any whole numbers or whole expressions or whole polynomials, and then remainder left over. And here's here's the point of partial fractions. We're taking a part and we're breaking that part down into its easier parts. Do long division, feeling this. But after we do long division, take the remainder and break him down further. So partial fraction says, take a proper fraction. If he's improper, divide first, but take a proper fraction. Simplified. Can you be broken anymore? And how do you break it down? Here we go. This is where we find our partials. The first step is just like a sometimes we need to actually break it down first. Sometimes we need to say, whoa, you're improper. Let's get all the whole parts out first. Let's see the remainder left over, and then let's break down those parts into the smallest, most basic partial fractions possible. So factor the denominator. Factor the denominator completely. And steps 3 and 4 actually say form partial fractions. Form partial fractions. And technically, this is just how to set up the procedure. To find the partials right now, this is just the setup. What's coming next is the solve. This is just the setup right here. To factor the denominator, form partial fractions for linear factors and form partial fractions for quadratic factors. Not every factoring has both. Some factoring will just have this. And if they're linear factors, they could look like something like x plus a or x minus a. They could look like something like 2x plus, or I could even say ax plus b. There could be a number in front of the x. There could not be a number in front of the x. There could even be for linear factors, and this is where it gets really weird. A factor raised to a power. And if it's raised to a power, we actually make a partial for the highest power and all the ones before that, counting down all the way to 1. So if this was a cubed, I would actually go 1 more. Linear, what I'm talking about is what's on the inside. When what's on the inside, x only has a power of 1, a degree of 1. What's on the inside only has a power of 1. Now, I guess I kind of used a twice, and that's kind of annoying because it doesn't have to be the same number. So let me put like a d over here. So here's the idea. If you guys look back at the problem that we just looked at a second ago, we could have factored this and we could have made it x minus 3 and x plus 2. We would have made one partial for one factor, one partial for another factor, but the dilemma is, well, how do we get those guys? So, we're in math. If we ever don't know anything, what do we make it? A variable. So after we figure out what the partial fractions are going to look like, then we make variables to say, all right, we better go figure out who the numerators are, because without them, we're stuck. And that's where the solving procedure comes in, which we'll see in just a second. However, every now and then, not only will you have factors that in the inside are linear, whether or not they're raised to higher powers, it's okay, they're still linear on the inside. Whether or not there's a number in front, it's still linear. But every now and then, you might get something that's what we call an irreducible quartic. We used A and B and C and D. E is its own number. Let's use F. And I can give you an example on the board. If this is too hard to think about, I can give you an example of one of these factors like x squared plus 4. If I told you to factor x squared plus 4, oh, it should be x plus 2, x minus, no it's not. That's x squared minus 4. But how do you factor that? Zeros, I bet that would help. So if we find the zeros, x squared equals negative 4, x equals plus or minus square root of negative 4. X equals plus or minus 2, huh? Are there any real ways? What does that mean? There's no factoring. Unless we're going imaginary, we're not. So we're stuck. If you're ever stuck with a quadratic factor that can't go down anymore, we're going to make him his own partial fraction. And instead of putting just an a or a b or a c or a d that technically have x to the 0, which means they're not top heavy because their degree is lower than, I'm going to also keep it not top heavy, but now I don't have to go to x to the power of 0. I can go x to the power of 1, which means I can have something like an x term and a constant term. And it's still not top heavy because there's a squared down there which is bigger than that guy. I couldn't put an x or else it'd be tied and I should go divide some more. I can't put an x squared or else I should divide before I do partial fractions. But as long as I keep it to where the bottom is heavy, not the top, I'm good. But that's just the setup. That's the setup. So what haven't we talked about yet? So guess what we're going to do? we're going to stop. We're going to go do one, and then you guys are going to help me with what the solve is. You ready? Okay, so what if we're going to go here? Don't worry, the big ugly page we'll talk about on Monday, and even then. Wait, this is the beginning problem. Yeah, it is. But let's pretend we don't know the answer. Is it top heavy, yes or no? Oh, okay, don't have to divide. Skip straight to the setup. The setup says let's factor. We don't need to divide. Let's factor the denominator. So we have x minus 3 and x plus 2. You guys agree if we were just to go from here forward, we're not looking backwards, we're not doing what we did at the beginning of class. We're going forward. So we're taking that denominator, we're factoring him. And once we factor him, what can we form? A partial fractions for each factor. Partial fraction for each factor. This is x to the power of 1. What do I need on top? Not to be top heavy. Can't be greater than or equal to. I need an x to the 0, which means I need just a constant. No x terms are allowed. There's an x term. It's not partial. But how do I solve for a and b? We've been doing all this work with systems, and with systems with two unknowns, we need two equations. Well, first of all, hold on. What don't we like? Fractions. Oh! How do we get rid of fractions? Oh. And don't we have to multiply everything by the denominator? So if we multiply everything by the denominator, x minus 3 times x plus 2 would get rid of this whole denominator, true? But what I do on one side, I have to do on the other. But remember, there's that addition. So whenever we see addition, what do we do in math if we're multiplying the entire expression? Don't we have to multiply both? So technically, we'll end up with a over x minus 3 times x minus 3x plus 2. And some of you could do this in your head, I know. Some of you might have done this way back up here in this step and not written it 2 times. But long story short, I have to distribute this multiplication. And the point of distributing and there being a common denominator is that what's going to happen when I multiply? Stuff is going to cancel, but isn't stuff also going to remain the same? So ultimately, we're going to have 1x, why did I write a 1, plus 7 is equal to a x plus 2a plus bx minus 3b. I still just see one equation, 2 unknowns. And there's an x that makes it even more confusing. But wait. Isn't that an x and that an x and that an x? And isn't that a non-x and a non-x and a non-x? Don't I have 2 different clues? One clue is where the 1x came from. And the other clue is where the non-x's came from. I do have 2 equations, 2 unknowns. Wait, but he has an x. But they all have an x. So what could I do? Basically, factor out an x and divide. What I end up with is 1 equals a plus b. So what are we going to do to solve? System of equations, substitution, elimination, row reducing, I don't care, you pick one. I'm going to finish off the example. You guys can go ahead and go to nutrition. But this example will be finished at the end of notes. Homework is not due, until Tuesday. But if you can start, it'd be a great idea. And if you're like, I really wish I had just heard a little bit more, go back a year. Around the we were doing partial fraction. Go ahead. I'll see you later. 1 times 3 plus 7 is 10.